Hello, everyone. My name is Sindhu Kaimal, and I am a student in the Discovery and Learning with Big Data class. This is my final project for spring 2026. So, for the first section of our project, I focused on a strategic enterprise level view centered on transforming credit card operations using machine learning. It explores how advanced data and AI capabilities can modernize decision making across the entire application lifecycle. My goal was to create a faster, smarter, and more secure system that delivers both business value and improved customer experience. So, as you know, American Express is a global payments company with over 110 million active cardholders, operating at a large international scale, and it is listed publicly. The company operates in a highly regulated consumer finance sector requiring strong compliance, credit risk modeling, and continuous digital transformation to stay competitive. It faces intense competition from both traditional players like Visa and MasterCard and fintech disruptors like PayPal and Stripe, all using machine learning for faster approval and better fraud detection. This slide highlights the core challenges in traditional credit and fraud systems. Decision making is still too slow because it relies heavily on manual and rule-based processes, which can't keep up with the modern fintech expectations. At the same time, fraud is becoming more sophisticated, requiring real-time and intelligent detection that legacy systems struggle to provide. On top of that, gaps in predictive modeling and poor customer targeting are leading to risks and lost acquisition opportunities. The solution transforms the credit decision process into a real-time, end-to-end ML ecosystem that is faster, smarter, and compliant. It combines smart credit models, real-time fraud detection, and customer intelligence to improve approval accuracy while reducing the risk. Together, these components create a seamless system that not only protects the business, but also enhances customer acquisition and retention. So this slide explains why this strategy is a strong fit for American Express, given its scale, regulatory environment, and competitive landscape. At this scale, the company needs real-time, low-latency decisions and a robust ML ops setup that can handle both batch and streaming data efficiently. Regulatory constraints like fair lending and AML require explainable models, auditability, and continuous monitoring, which shape how solutions must be designed. At the same time, rising competition from fintechs and digital-first players makes advanced ML, faster approvals, and personalized experiences essential to stay relevant. So again, in this slide, I'm outlining the end-to-end technology ecosystem that is required to support scalable real-time machine learning systems. The stack combines modern-day infrastructure like Snowflake or Databricks with Spark, Kafka, and Airflow to handle both batch and streaming workloads efficiently. On top of that, critical subsystems like the decision engine, feature store, and fraud detection ensure low latency, consistent, and intelligent predictions. Finally, strong model governance and data pipelines enable reliability, explainability, and continuous monitoring in a highly regulated environment. Both people and models need to be aligned to make the system work end to end. Each role, from data engineers to compliance, has a clear responsibility, ensuring data pipelines, models, deployment, and regulatory checks all function together smoothly. On the modeling side, different ML techniques are mapped to specific business problems like credit approval, fraud detection, and customer segmentation to ensure the right tool is used for each task. Together, this alignment reduces silos and creates coordinated, scalable approaches to delivering business impact with machine learning. So I use a phased approach to building and scaling the solution, starting with a strong data and modeling foundation, then moving into real-time decisioning, and finally, enterprise-wide optimization. Each phase builds on the previous one, reducing risk while steadily increasing business impact and system maturity. The expected outcomes include faster credit approvals, lower fraud rates, improved prediction accuracy, and stronger customer acquisition while maintaining full regulatory compliance. A clear vision of faster decisions and smarter intelligence and safer systems are provided by machine learning. By aligning technology, data, and people, the traditional credit process evolves into a modern, scalable system. The end result is a strong competitive advantage driven by speed, accuracy, and customer experience. Now, moving on from financial systems to a real world data case, focusing on the Austin Animal Shelter dataset. The goal here was to show how raw, messy data gets transformed into clean, structured data that's ready for modeling. The raw data set contained over 95,000 records, 10 variables, and spanned data collected between 2013 and 2020. The variables included a mix of identifiers, dates, categorical features like animal type and breed and their color, and text space fields that required transformation. The key objective was to clean, remove redundant fields, and convert these variables into a structured format that is suitable for analysis and modeling. So I kind of built a structured pipeline that systematically transformed raw, messy data into a clean, model-ready data set, starting off with loading and inspecting the data, then removing redundancies, standardizing formats, and handling missing or invalid values. The final step was to ensure that the data set is verified and saved, making it reliable and ready for downstream analysis or machine learning. So the process begins by pulling the data and quickly profiling its structure to understand what we are working with. From there, non-informative fields like IDs and redundant time features were stripped out since they don't add any predictive value and only introduce noise. After removing a small set of duplicate records, the data set became leaner and more reliable, setting a clean foundation for deeper transformation. Dates were transformed into a proper date-time format, enabling precise extraction of day, time, and age-based calculations. Age was then converted from text into a consistent numeric feature like months and years, making it usable for modeling. Here, the text fields were standardized by converting them into lowercase, which removes all the inconsistencies in the case, like uppercase versus lowercase, and ensured that they were all uniform. Missing values were carefully handled by identifying nulls and removing a small set of incomplete records. So the data integrity was preserved without heavy imputation. Finally, invalid entries like 0 or negative ages were filtered out, eliminating impossible values and improving the reliability of the data set for analysis. Before wrapping up, The data set went through a final validation to ensure everything was consistent and trustworthy. The clean data set now consists of 89,465 high-quality records across 11 well-structured features and 0 missing values. It was all fully validated. The data types were validated, and noise was reduced by removing duplicates, non-predictive identifiers, redundant fields, and invalid entries. The age distribution was heavily skewed, so all these were observed in case we needed this data set for future modeling. So from messy records to a cleaned structured data, the foundation was strong enough to support reliable insights and modeling. With quality data in place, the focus could now shift confidently to extracting value, building models, and driving meaningful decisions. Now, transitioning into a new problem space, we are focusing on the predicting the abalone age using machine learning techniques. This project highlights how physical measurements can be transformed into predictive insights, showing core modeling concepts in a real-world data set. The initial data exploratory analysis gives a clear view of its structure, size, and key variables. The dataset included about 4,000 records with 9 features and targeting the number of rings as a proxy for age. There were no missing values at the start. Distribution patterns, however, revealed some skewness and presence of outliers. So they needed careful pre-processing before the modeling. The pre-processing stage focused on making the data set consistent and model ready by addressing gaps and formatting issues. Missing or zero values were corrected using median imputation, while categorical variables like sex were transformed into one-hot encoding to make them usable for machine learning models. Finally, the data was split into training and testing sets, ensuring that a reliable evaluation framework for model performance was available. I chose linear regression here because the target variable is continuous and fits naturally with a regression approach. It also provides clear, interpretable coefficients, making it easy to understand how each feature impacts age prediction. So as a baseline model, it offers a fast and simple way to evaluate performance before moving to complex algorithms. For our results, the model explained about 53% of the variance, showing a moderate predictive power, but clear room for improvement. Features like diameter, hole weight, and height were positively influenced the outcome variable age or rings, while shaft weight and visceral weight showed negative relationships, indicating more complex underlying patterns. Prediction errors were reflected by an RMSE of 2.3, suggesting that the model captures general trends, but it struggles with high variance cases, especially for older creatures. So the model delivers a moderate fit with an R square of 0.535 or 53.5%, meaning it captures general trends but not all variability in age. Validation results indicate stable and consistent performance, confirming it as a reliable baseline rather than an overfit model. Moving forward, improvements will focus on reducing multicollinearity, exploring nonlinear models, handling outliers more effectively, and hyperparameter tuning for better accuracy. Now let's move on to the classification problem focused on predicting income levels using the adult salary data set. This project demonstrates how demographic and socioeconomic features can be used to model and classify whether an individual earns above or below a threshold. This project works with the adult salary data set containing over 48,000 records and 15 features spanning demographic and socioeconomic attributes. The goal was to classify individuals into two income groups, predicting whether their earnings fall above or below $50,000. By using features like education, occupation, and work hours, the model aimed to uncover patterns that influence income levels. This stage of data discovery and analysis focused on understanding the data set structure, distributions, and data quality issues before modeling. Key patterns showed that a wide age range, diverse education levels, and a mix of numerical and categorical features, along with some class imbalance in income groups. Data quality checks highlighted missing values in a few categorical fields, which were addressed through imputation, while irrelevant features like final weight or FNL-WGT were removed to improve model performance. The workflow started by addressing missing data and replacing ambiguous entries like question marks with proper null values and imputing categorical fields using the most frequent values. Next, non-informative features such as FNL-WGT were removed to reduce noise and improve the model focus. Finally, both the target and categorical variables were encoded, ensuring that the data set is fully structured and ready for machine learning without multicollinearity issues. So for this project, I selected logistic regression because the problem is a binary classification task, making it a natural and effective starting point. It also offers strong interpretability, allowing a clear insight into how features influence income prediction while remaining computationally efficient. The training setup uses a 67 to 33% split with tenfold cross-validation, ensuring that the model is both reliable and generalizable. The model achieved an overall accuracy of 83.5%, with strong precision and recall for the majority class, that is less than $50,000, indicating that it reliably identifies low-income cases. However, performance drops for the minority class, that is the greater than $50,000, where recall is significantly lower, highlighting the impact of class balance. Cross-validation results remained stable, confirming that the model is consistent, but improvements were needed to better capture higher income predictions. Now, the model translates real-world profiles into clear income predictions based on learned patterns. It performs well overall, but the imbalance between income groups highlights the need for techniques like resampling to improve minority class detection. The model is a strong baseline with clear opportunities to enhance accuracy and fairness in future iterations. Moving on to the next project, I used k-means clustering for an unsupervised learning problem, focusing on car evaluation. The goal was to uncover natural groupings in the data to better understand patterns in car acceptability and features without predefined labels. So this project works with the car evaluation data set, which includes about 1,728 records with 7 key attributes describing different aspects of a car. The focus is on features like price, maintenance, safety, and capacity to understand how they collectively influence overall evaluation. So, using unsupervised learning, my goal was to uncover natural groupings in the data and reveal hidden patterns without relying on predefined labels. The data shows that most feature categories like price, maintenance, safety, and luggage are evenly distributed, which helps to prevent bias during clustering. However, the evaluation outcomes are highly imbalanced, with nearly 70% of the cars labeled as unacceptable and very few in the higher quality categories. This contrast highlights a challenge where balanced inputs are needed to, or balanced, where balanced inputs still lead to skewed outputs, making it important to interpret clusters very carefully. The pre-processing pipeline ensured that the data was clean, structured, and suitable for clustering algorithms like k-means. Ordinal features were encoded in a meaningful way, preserving their natural order so the model can interpret relationships correctly. Feature scaling brought all the variables into a comparable range, preventing any single feature from dominating distance calculations and improving cluster performance. K-means was chosen because it is simple, efficient, and works well with this data set once features are numerically encoded. So to determine the optimal number of clusters, the elbow method was used by plotting SSE against different values of K. The clear bend at K equals 4 indicated that the best balance between model simplicity and cluster separation, aligning well with the underlying evaluation categories. The clustering results show a low silhouette score of 0.1577, indicating weak separation and significant overlap between the clusters. Some clusters, like cluster 1, clearly capture poor quality cars, while others remain mixed, reflecting less distinct boundaries in the dataset. So while k-means identifies general patterns, the results suggest that more advanced methods or feature engineering might be needed for clearer segmentation. These examples make the clusters more tangible by showing how different feature combinations translate into real-world car profiles. So these were the predictions. Affordable, safe, and practical cars to group into positive clusters, while expensive, low safety configurations fall into clearly unfavorable segments. Overall, the results reinforce that clustering can provide meaningful segmentation insights, even if boundaries between groups are not perfectly distinct. Now, bringing everything together, comparing how different models perform across regression and classification tasks. So the focus is on understanding trade-offs in accuracy, interpretability, and use case fit to choose the right model for each problem. I'll begin with the linear regression, the abalone data set. Uh, the data set had a clean starting point with 4,177 records and 9 features capturing physical measurements of the abalones. The target variable rings, which served as a proxy for age, linked measurable attributes to a meaningful prediction outcome. Early analysis highlights skewed distributions and multicollinearity among related features. So, which said that there is a careful need for pre-processing before modeling. Now, when comparing linear regression with the decision tree, the results clearly show a strong performance gap between the two models. with linear regression significantly outperforming the decision tree. Linear regression achieves a high explanatory power, like at 53.5 percentage, whereas decision tree was much, much lower. Linear regression also achieved lower error, making it more reliable for predicting the age. In contrast, the decision tree struggles with poor tuning and overfitting, leading to weak generalization and less accurate predictions. Moving on to the second data set, which was the adult salary data set that was analyzed using a logistic regression and a KNN model. So this data set contained around 48,000 records and 15 features, providing a rich mix of demographic and socio-economic information for modeling. So missing values were concentrated in a few categorical fields and were handled through mode imputation and that ensured that minimal data was lost. So careful encoding and pre-processing steps help to create a clean, leakage-free data set that was ready for reliable model training and evaluation. So now comparing the model results, logistic regression versus the KNN or the nearest neighbor, where I chose K to be 5. This comparison highlights that KNN slightly outperforms logistic regression, achieving higher accuracy and better cross-validation consistency. It also shows improved recall and F1 score for the minority class, that is the higher income individuals above $50,000, indicating a stronger performance in that class. Overall, while both models are solid, K nearest neighbor provides a better balance between accuracy and minority class prediction. So both projects show a clear pattern where simpler baseline models are kind of outperformed by more suitable or better tuned alternatives. Linear regression and K nearest neighbors emerge as the stronger choices in each of the project categories, and they deliver better accuracy, lower error, and more reliable prediction across their respective tasks. A common theme is that model selection, tuning, and handling data challenges like imbalance or overfitting are critical for unlocking better performance. So once again, to reiterate, linear regression was better suited for the abalone project and KNN for the adult salary project. So they were the strongest performers and each was better suited for their respective problem types than their alternatives. The results reinforce that model choice, proper tuning, and handling data challenges like imbalance are key for achieving reliable performance. Overall, consistent data validation confirms these findings are stable, and consistent validation, the tenfold cross-validation, confirms that these findings are stable and not driven by chance alone. Thank you.